We're continuing today at looking at problems related to related rates. We started looking at those yesterday, and we saw that we might have some application where we have a function that is in terms of time, and we might have multiple functions going on that are in terms of time. And when we differentiated both sides of the equation and we differentiated our variables, we had to remember that they were with respect to time. And we needed to use implicit differentiation. The example in front of us states that we have a 13-foot ladder that is leaning against a house when its base starts to slide away. Dangerous. You don't want that happening when you're on the ladder. Anyways, by the time the base is 5 feet from the house, the base is moving away at a rate of 36 feet per second. So look at part A, what is the rate of change of the height of the top of the ladder? So first thing with these, we want to draw a diagram. And we have this ladder that's leaning up against the wall. I don't like how thick that is. We have a ladder that's lining up against the wall. What color should our ladder be? And we're given that this is 13 feet. We're given that the base starts to slide away. So let that be X. Let this be X. And the base is 5 feet from the house. So we're going to look at an example when this length right here is equal to 5 feet. But what our ladder is sliding, that base is getting longer and longer. And the base is moving away at a rate of 36 feet per second. So we know that dx dt is equal to 36 feet per second. Okay, and so what is the rate of change of the height of the top of the ladder? Well, we need to figure out what that height is. So let that height maybe be y. And we have this ladder. We have a right angle, so we can use our Pythagorean theorem. And so I know that y is equal to the square root of the hypotenuse squared, 13 squared, minus that base squared, so 5 squared. Everybody okay with that? We're just using the fact that in our case, 13 squared equals 5 squared plus y squared. Subtracting 5 squared, taking the square root of both sides. So we have the square root of 169 minus 25, which gives us the square root of 124, which is equal to 12. And we're in terms of feet. So what is the rate of change of the height of the top of the ladder? Well, let's write this out. We know that 13 squared, that length of the ladder is never changing, is equal to x squared.
Stop singer.
Wait, what?
120, the square root of 124 is not 12.
Oops. Sorry.
Yeah,
It's like 11, it's like 11 point something.
Oh, darn it.
169
I'm
minus
thinking
25
144.
equals
Yeah. Okay, you're right. But the thing is that the transcription is in the way. Let me just, well, let's just go back here. Did I do that right? That should be 144 though, right? That's what I went wrong.
Yeah.
Okay, so 169 minus 25 is 144. And that square root is 12. Okay, thank you. Plus y squared. So let's differentiate both sides of the equation. Well, 13 squared, which is 169, is a constant. So when I take the derivative of a constant, we get back 0. Is equal to, well, the derivative of x, but that length of x, it's expanding as time goes on. So that's a function of t. So this is 2x times the derivative of x, which is dx dt. Plus the derivative of y squared, which is 2y, but y is also a function of time. And so we have to write dy dt. We're looking at finding the rate of change of our height, dy dt. So for part A, we want to find dy dt. So we could subtract that 2x dx dt on both sides. And so if we did that, we get this 2y dy dt is equal to negative 2x dx dt. And we're trying to find this rate of change when this base is 5 feet. So we have these values for our x and y. Maybe let's first divide through by 2y on both sides. And if we divide through by 2y, notice that our 2's are going to cancel. And so we get dy dt is equal to 2's cancel. So we're just left with a negative x all over y dx dt. Well, we know that, again, that the base, which is our x value, is 5. So we have dy dt equals this negative and then 5 all over y. We just found out our y value when our base is 5 feet is 12 feet. And all times dx dt. And we know dx dt, the rate that change that the base is moving is 36 feet per second. So all times 36. Okay, so let's just simplify that. I noticed 12 goes into 36 evenly 3 times, and then multiplying that 3 times that negative 5. Oops, I didn't mean to do that. We get that dy dt is equal to negative 15. And it's feet per second. So notice that the base has a positive rate of change, but that base is growing as the ladder falls. That height, though, as the ladder's falling down, is getting shorter. It's decreasing, and so that's why we have a negative. So that's part A. Part B, same picture, but this time we want to look at the rate, at what rate is the area of the triangle formed by the ladder of the wall and the ground changing then? Well, so we just need to change our formula. So for part B, we know that the area of a right triangle is 1/2 times base times height. So, but in our case, our base we let be x, right? So area equals 1/2 times x times height, and the height in our case is y. And we want to find the rate of change of area. So we want to find dA dt is changing. So I notice when we take the derivative of both sides, we have x times y on that right-hand side. And so we're going to need to use that product rule. So I'm going to move this over for now. So taking the derivative of a, we have dA dt is equal to 1/2 times, so the derivative of x, that gives us 1, times the derivative of the inside, dx dt, times the second function y, plus 1/2 x times the derivative of y. And the derivative of y is 1 times the derivative of the inside, dy dt. Well, we already know a couple things. We already solved for what y was, and that was 12. We know that the rate of change that the ladder is falling, that base, that was 36. And so we can start plugging in these values. So let's just do that. So we have dA dt equals 1/2 times 1 times dx dt, but the rate of change again, that the ladder is falling. The base is moving at 36 feet per second, times y, which we found to be 12 feet, plus 1/2, times our base, which we were given to be 5 seconds, times dy dt, which guess what we just found, dy dt. So at that time, our rate of change of our y value is -15. Okay, so 2 goes into 12 6 times, or I can say 2 goes into 36. It doesn't matter. I'm just going to simplify this down. So 2 goes into 36 18 times. And I have 18 times 12, which gives us 216. So we have 1/2 times 5, which is 5/2. But 5 times -15, that gives us 75. So this is actually minus. And I probably shouldn't have gotten rid of my common denominator. It's okay. We'll have to just go get it again. So this is minus 75/2. Okay, so getting a common denominator. So we have 216 times 2 over 2. That gives me 432 over 2 minus 75/2. Which gives me 357 over 2, which gives us 178.5 square feet per second. So that's the rate of change when the base is 5. So one more part of this question, and this is asking us at what rate is the angle between the ladder and the ground changing then? Let's look at C. So it's the rate of change of this angle. So the rate of change of the angle between the ladder and the ground. I just needed to know where theta was. So this is theta. So we want to figure out what d theta dt is. So let's look at this. And sorry, let me just look at one more time. I believe it's with the ground. So that rate of change of the ladder. Okay, so let's look at this. We know our trig functions. So our trig functions for a right angle, we have x, which is 5 feet. That's what we're looking at, and hypotenuse. We can use other trig functions too, but let's use cosine. So cosine of theta, remember, is equal to adjacent x all over the hypotenuse, which in our case is 13. So let's take the derivative of both sides. And so the derivative of cosine theta, that's negative sine theta, is equal to, well, derivative of x is 1 times, we can think of this as 1/13. So this is just going to be 1/13 dx dt. I forgot one thing. When I took the derivative of cosine theta, theta is changing with respect to time, so I should have d theta dt there too. So this is negative sine theta d theta dt. Okay. So we can divide both sides by negative sine theta. We can put in our values. We need to find theta actually when we have the following information. So this is 5 and this was 13. Not 13, that was 12. It doesn't matter which trig function I use. So here we know that cosine of theta is equal to adjacent, which is 5, over hypotenuse, which is 13. So we can find theta by taking the cosine inverse of both sides of 5/13. Okay, so we have d theta dt is 1/13 times the rate of change that the ladder is moving at the base, which we saw was 36 feet per second. We're going to divide by our negative sign. And our theta value we just saw was cosine inverse of 5/13.
Wouldn't it just be easier to find sine of theta using
Yeah,
the
I also
triangle?
wanted to, yeah.
So
I
sine
also wanted to
theta,
know.
okay. So sine theta though is opposite, which is 12 all over 13. Okay, that makes more sense because then when we have the sine inverse, right, the sine and the sine inverse will cancel. Is that why you're saying that? So theta here is equal to sine
Or
inverse of 12/13.
couldn't we just plug in the sine theta equals 12/13 and divide the 36 over 13 by negative 12/13?
Oh, I guess we could do that too.
Yeah, because we don't need theta, we need d theta,
Yeah.
dt.
Okay, so that's going to happen too when I plug this in, which would have given me the same thing that you guys had just said, and then we don't have to deal with, well, I guess I'm still dealing with an inverse for a second. Because sine and sine inverse cancels us out, just leaving us with an argument, which is 12/13 here. And so you would have had negative 12/13 right here and divided by it, and we'll get the same thing. So good call. D theta dt is equal to 13 goes into 36. Does it go unevenly? No. So we have 36/13 divided by negative 12/13. And let's invert multiply by the denominator. So this is 36/13 times negative 13/12. So 13's cancel, 12 goes into 36 3 times. And so we have, that is negative 3. And this is radians per second.
So do we got to convert to degrees?
Did it ask for degrees? If it
Okay.
didn't, I would leave it like that. I can also look at what my math lab says. Yeah. I don't think so.
It doesn't ask for it. It
Yeah, I
says
think
leave it in
I'm a-
radians.
Yeah, I
Okay.
think MML does radians.
Okay, thank you. In our next example, sand falls from a conveyor belt at a rate of 9 meters cubed per minute onto the top of a conical pile. The height of the pile is always 3/8 the base diameter. How fast are the height and the radius changing when the height or the pile is 8 meters high? Okay, so sand is pouring down off a conveyor belt and we're getting some circular cone. We have our radius and we have this height in here. So let's go through and pull out pieces. And so the conveyor belt, the sand falls at a rate of 9 meters cubed per minute on top of the conical pile. Okay, so that is the rate. I believe that that volume of the cone is filling up. So let's say volume, so dV dt is equal to 9 meters cubed per minute. This is going to help us. The height of the pile is always 3/8 of the base diameter. Okay, so we know that the diameter is equal to 3/8 of my height, h.
Wait, wouldn't it be the height is equal to 3/8 of the diameter?
Let me read it again, thanks. So the height of the pile, the height is always 3/8, yep. Of the diameter. So how fast are the height and the radius changing when the pile's 8 meters high? So let's rewrite height. Let's see. Diameter is half of the radius. So let's look at this height as in terms of radius. So 3/8 times 1/2 r. So our height then is going to be 3/16 of our radius.
Wait, wouldn't it be r equals 1/2 d?
Oh my gosh. Yeah, it's 1/2 of our radius. Half of our diameter is our radius. So let me go back. And so D is the same thing as twice our radius. I know that. And so that actually simplifies because 2 goes into 8 4 times. And so we have 3/4 R. And we're in meters. Okay. So that's the height. when, and the radius changing when the pile is 8 meters high. And we want to find dH dt and we want to find dr dt. So we need to pull in an equation. And we have the volume, we need the volume of a cone. So the volume of a cone, which I wrote down before we started, is pi times r squared times h over 3. Well, I have my height here is 3/4 r. So let's replace what h is. So our volume then is equal to pi times r squared. I'm going to just move this as 1/3. And h was this times 3/4 r. So our volume then is pi, our 3's cancel, and we're left with r squared times r in the numerator, which is r cubed, all over 4. But we can put the 4 over the pi, under the pi. So let's take the derivative of both sides. So dv dt is equal to, so now when we take the derivative of pi force r cubed, bring our 3 down front, we get 3 pi force. Subtract 1 from our exponent, r squared, times the derivative of the radius with respect to time. Okay, so what do we need? We need to know what r is when our height was 8.
Couldn't we take that equation h equals 3/4 r and then
Right,
solve
right, exactly. So we're going to go into this equation that we have. We're going to plug in 8 for h is equal to 3/4 r, and I'm not going to put the meters in there. So if I multiply both sides by 4/3 to cancel my fraction, that's going to give me 32/3. Okay, so let's go back in here and let's solve for, we're solving for dr dt first. We know what the rate of change is for our volume. That was 9 meters cubed per minute. So we have 9 over here is equal to 3 pi force times our radius, which was, we just found to be 32/3. This is squared times dr dt. I'm just going to rewrite 32 cubed squared as 32/3 times 32/3 dr dt. Because I noticed that 4 goes into 32 8 times, just reducing things. I have a 3 here, so that's going to cancel with one of my 3's. So I have 8 times 32 9 equals, so that's 16, carry my 1, that's 256. I still have my pi all over 3 drtt. So we can invert multiply, right? And so we have dr dt is equal to 9, invert multiply. So that's gonna be 9 times 3, which is 27 all over 256 times pi drtt. I want to just see how they want their answer. Okay, so when I was doing this, I was right to get dr dt by itself. I multiplied by 3 all over 256 pi to the 9. And so I shouldn't have had dr dt on that one side. So right now I'm keeping it as the exact answer. And this is the rate of change of our radius. So the radius is going to be growing meters per, I believe this was minutes. So meters per minute. Okay, so they did end up rounding it in terms of decimals. So 0.336 minutes per minute is the rate of change of our radius. But we still need to find the rate of change of our height. And so we need to go back to our equation. So recall that our equation for our volume is equal to pi r squared times h. We had gone in there and we had replaced what h was. But let's instead, this time, let's rewrite r in terms of h. So if we're given that our height is equal to 3/4 r, we can multiply both sides by 4/3. And so we get r is equal to 4/3 times h. So let's go back in and replace in what r is in here. And so we do that, we get the volume is equal to pi times r, which is 4/3 h. Quantity squared times h. So let's simplify that a little bit. So 4/3 h quantity squared, I still have my pi, 4 times 4, so that's 16 all over 3 times 3 is 9 times h squared.
Wasn't it h over 3? Pi r squared h over 3.
Yes. Yep, right here.
Or can we just differentiate this equation that dr over dt is d over dt for 4h over 3?
Let me just think about that, Gurjot. Okay, so question was, let's just look at this. We already have this formula in here where we have h is equal to 3/4 r meters. And so if we take the derivative of both sides here with respect to time, then we have dh dt is equal to 3/4 times r, derivative of r is dr dt. So dh dt is going to equal 3/4 times the rate of change of our radius with respect to time, which we did all that work right over here. And I'm just thinking if I kept it in, I'm going to keep it in actually for right now until the end. I'm going to keep that into exact. Is that going to help me? No. Okay, so I'm going to just, I was thinking that it canceled for some reason. It doesn't. So let's just multiply that by this then. 0.0336. And we get dHdt is approximately 0.252 meters.
So do we not include the M at all?
We will at the end, but that was just in terms of meters. If that was
Oh, okay.
length in terms of time or something, I would definitely include that. But that's just giving me my units. So now I'm going to include it in here that my rate of change in my height is, and I forgot a 0 after my decimal. So this should be 0.0252 meters per minute is what the height is changing. And the sand is pouring in, and so that cone is getting larger and larger. And so that height should be positive rate of change.